What I would like to do is, I usually do with my lectures, I would like to make a small step back, so pretty much go a little bit further back than the last line in this slide, the last thing I did yesterday. Simply because we need just to recollect what we were doing and maybe realize what we were doing, because the last bits of algebra that I introduced yesterday, it was late in the day, everyone was tired, so it might not get stuck in your memory. So, reminding you what we are trying to do. We derived the theory, we derived the equation, Rayleigh equation, and we realized that Rayleigh equation has solutions with certain properties, and specifically we were interested in growth rate. Rayleigh equation provides some knowledge, some information about what the growth rate of perturbation is, and without even solving that equation, we were able to derive a few criteria. So 2 criteria, Rayleigh criteria, so the second derivative has to be equal to the second derivative of a velocity field has to be equal to 0 somewhere in the flow domain. So inflection points should exist for instability to occur. If inflection point is not there, then no instability is possible. And then refined criterion, so another condition which involves the product of the second derivative of the base flow velocity profile and the difference between base flow velocity and somewhere in the flow domain and the base flow velocity evaluated at inflection point. And then we played with these criteria and considered multiple examples of continuous flows. So I just drew the continuous line with no corners and just traced the curvature. So the curvature was like that, whatever, and we considered various combinations, and we made conclusions which of those profiles can or cannot be unstable, and therefore which of those profiles are expected to be visible in reality and which of them might not be visible in reality. However, since we are working with a so-called inviscid fluid, literally that means that different layers of fluid do not know about each other's existence. So they just slide and they don't know that there is a neighbor there, right? If I come to the wall and slide my hand against the wall, I can feel it. And I can feel it because of friction. If the friction is not there, like when I'm walking on this floor, I'm almost falling down because it is very slippery and my shoes have a very slippery sole. So therefore, my sole does not feel the contact with the floor. That's why I'm slipping, right? So that's exactly the same concept with inviscid fluids. So different layers do not feel each other. They just slide over each other without knowing what happens to the neighbor. And because of that, if we adopt, continue working with inviscid type of model, which is idealization, then we formally can imagine velocity profiles like that, when sharp changes happen just at a point, okay, like that, sharp corners, okay? This is not prohibited by mathematics. So in reality, of course, we will see that this is never the case, but as a first step into trying to explain what is happening into modeling, that is acceptable. So, all right. But if this is the case, I can clearly create something like that consisting of straight lines. And as we looked at the equation, Rayleigh equation, so when we look at the equation as a Rayleigh equation, then the second derivative of the base flow velocity, in this case, well, it just vanishes. One of the terms quite a long way back. specifically this term here, vanishes, and whatever is left is just a product, and we discussed what happens, so we will get just a trivial solution then. So therefore, situations like that where we expect the corners influence the solution more than actually the bulk. In the bulk, everything is nice, everything disappears, but the curvature of the base flow velocity profile at these points is infinite, as we decided. So therefore, we have 0, 0, 0, 0, all of a sudden infinite. Again, 0, 0, 0, and again infinite. So we cannot really solve this equation. We have to break that equation into regions. And if we break it into regions, somehow the solution at the boundary of those regions have to match. Right? So therefore, instead of having a single problem for the whole domain, we have to break it into regions. So we will have to solve 3 problems. One here, and one here. That's what we need to do. And then, obviously, because all these 3 regions are part of the overall space, we have to match them together. We have to glue them together somehow. That's what we need to do mathematically. And then, of course, there should be some sort of gluing conditions, which are called jump conditions. So when you jump from one layer to another, you experience some change at the boundary, right? So you cross the boundary, so you're in one country, and all of a sudden you're in another country, so the rules change, culture change, you know how it works. So therefore, you need to adjust, and you need to make sure that your transition doesn't kill you, right? So you don't get shot at the border or explode on a landmine. And we introduced the concept of continuity of pressure. And this is because if the pressure is discontinuous, then you're stepping on a landmine, right? It's an explosion. So we cannot have those explosions. So therefore, pressure has to be continuous. And we looked at the expression, explicit expression for the pressure, and we have it. So therefore, we introduced the value of the pressure just above the corner point and just below it. And we compared them. The 2 values of the pressure must be equal to each other, so therefore the difference between them, that is denoted by this delta, must be equal to 0. So that is the physical condition. So, and then I went into this, and that's probably was not quite clear. So I told you that this is witchcraft, and it is to some degree. So I need to explain why I am doing that. So this is a physical condition, but why do I need to do all that? And that's where I pretty much stopped yesterday. I introduced that, but I was not quite clear about why we're doing that. And the reason is here. So if you look at this equation here, right, this equation, we are talking about continuity of functions, or discontinuity of functional jump for different functions. But how many functions do we have here? So u is known function. This is just some constant. du obviously can be determined. So it is either 0 in this part of the domain, or it is some non-zero value. In this case, it is, I chose it to be 1. So this term is also known. But what remains unknown? This, we don't know what that is, and this, right? If we don't know what that is, we don't know what its derivative is. So essentially, this is a single equation, but we have 2 unknowns. Is that clear? So we cannot solve that. We need one more condition, and that's what we are doing here. That's where the witchcraft comes from. So we need to add an extra condition, because pressure condition contains 2 unknown variables. Is that clear? Okay. So therefore, we need the second equation, and therefore we try to invent that second equation. And this is done by observation. So if I simply take the equation for the pressure and divide it by u minus c squared, then I will get this. Right? That's just simple algebra. We realize that we will see the quotient rule, and that's what we have. Now, let's look at the left-hand side. This is pressure. And we said that pressure must be continuous. Right? It must be continuous. So let's look at the denominator. We have u minus c, but c in general is a complex quantity. So therefore, this cannot be equal to 0. right? So therefore, it is continuous function divided by another function, which is continuous function, right? And the denominator is not equal to 0. So therefore, this is a continuous function, doesn't have any jumps. So if the left-hand side doesn't have any jumps, so the right-hand side must not have any jumps, right? Otherwise, they will not be equal to each other. So then we say that this is a continuous function, and we can integrate a continuous function. And that's what I'm trying to do that. So I'm trying to integrate this equation over the region which is very close to the corner, right? To the boundary between two sublayers. Okay, so that's what that epsilon does. So essentially, I start slightly below and I finish slightly above that corner point, and I integrate that. And of course, integrating derivative is simple. So what I have is just the value of the function that I integrate, evaluated at z0 plus epsilon, z0 minus epsilon. So that is my delta. Okay, so that's what that is. But that must be equal to the integral of this function, right? If I integrate right-hand side, I have to integrate the left-hand side. So integrating right-hand side is fine because it's just dropping the derivative. Integrating the left-hand side is impossible because we don't know what p is. But we know that this is continuous function. So if the function is continuous and you integrate it over very small width or length, what do you get? So what I mean here, so let me just add another slide. So you have a function. And the graph of the function, it might be some irregular function, might even have corners, something like that. So, but this is your z, so this is your z0. And this is z0 minus epsilon, this is z0 plus epsilon, right? So you have this interval here, right? And you integrate this function over this small interval. So what do you get geometrically as a result of that? You will get this area, right? Now, because that function is continuous and it is non-singular, it doesn't go to infinity, we decided on that. If we start shrinking the width of this interval, if epsilon goes to 0, what happens to the area? Well, it will shrink. Well, we will have the same height as before, right? Or a finite height, but it will be multiplied by 0. You will get 0, right? So therefore, coming back here, we conclude that this, which is a result of integrating the right-hand side, in the limit must be equal to 0. Is that clear? Right? So, all right, so basically what we've done here is we realized that we have two unknowns rather than one, so we had to have the second equation. Then we realized that the pressure equation can be written in this form. Then we realized that we can integrate it. And if we integrate the right-hand side, it is just directly that. But if we integrate the left-hand side, we don't know what that is algebraically, but we know in the limit it got to be 0. So therefore, this is 0. So now we have this condition, we have this condition, and we have the equation that we derived previously, which is Rayleigh equation. So therefore, what I will do now is write final formulation of the problem in algebraic terms. Okay, so I'll just copy it for you so that it is the whole thing is in front of you. So just to make sure that I do not miss anything. So which form did I use? So what I would like to do, I would like to simply write all equations that we need solve on the same page, and I copy and paste this equation, and I will add the boundary conditions, and I will add jump conditions. So u bar minus, and we decided that this will be just c, to simplify the notation, d squared psi hat minus alpha squared psi hat minus psi hat multiplied by d squared u bar is equal to 0. Then let's just go back and specify the boundary conditions. So what we have here, so that's the difference to what we did before. We do not consider the plates anymore. We allow these to extend to plus and minus infinity. Okay, so that's the geometry. So the boundary is moved from z equals 1/2 to z equals infinity. Okay, so now let us think what we would expect to happen at infinity. So if there are perturbations at infinity, what would it mean physically? So any perturbation is a physical object. For its existence, for its propagation, you require what? Physically. So to create anything, you need what? And force comes from where? So force does not, well, if you're driving a car, where does the force come from? So what moves the car? Do you ever go to a petrol station? Yes, you probably do, right? So you need to fuel that. What's fuel? It's essentially a source of energy, right? And how much fuel can you put in your car? Limited amount, right? So when you drive through the air, you push the air, and your energy which you had put in, right? So you put your petrol in, and as you move, you're essentially wasting your energy or spending your energy to overcome the resistance of air or friction and so on and so forth, and the heating and the, so you have a limited supply of energy. You never ever have infinite energy. So therefore, if you consider infinite domain, it would only have physical relevance, so the problem would have physical relevance with infinite boundaries if we assume that the amount of energy is somehow limited. Because if we have perturbations propagating all over the space, you need infinite energy to create them. You don't have that. So therefore, the physical condition is that as we go further away, perturbations somehow should vanish, right? So it's just not enough energy. If at all, if anything at all, something will be happening here, but as you go to infinity, you can afford to have much there. So our perturbations here are pretty much given by this function psi, right? Stream function. That's what the algebraic characterization of the perturbation field or disturbances is, right? So therefore, we conclude that as we go to infinity, we have to lose that. That has to become 0. No other way. Otherwise, we will just run out of energy. Is that clear? So that's physical. It's not mathematical. It's purely physical explanation. All right, so therefore, I will need to add the following boundary conditions. So as we go further and further away, we will get oops, not phi. Psi hat tends to 0 as z tends to plus or minus infinity. So that's physical condition. That's physics for us, right? That's what we have. And then we have the jump conditions. And the jump conditions are delta of u bar d multiplied by psi hat minus u bar multiplied by minus c d psi hat is equal to 0, and that's the pressure continuity condition. And the other condition that we just derived is that psi hat over u minus c jump of this is also equal to 0, and this has to be true at both corner points, z equals 1 and z equals minus 1, right? Okay, so now our problem formulation is complete, and what I would like us to do next is to solve this system of equations, including the Rayleigh equation and the jump conditions and the boundary conditions. So, what I will ask you to do now, and please do that clearly so that you can understand what you are doing for the final day. So, you have this system of equations that is in front of you. It will be unfortunately in different screens here, so I will have to jump in between them, but hopefully you will just start this on the top of the page. So it is always in front of you. So, and this system of equations needs to be solved in each individual regions. And those regions are region A, z greater or equal than 1. Region B, minus 1 greater or equal to z, oh sorry, less or equal than that. Less than 1. And C is z less than minus 1. So you have 3 regions, and you need to solve this problem there. So in here, you have u bar is equal to 1. In here, you have u bar is equal to minus 1. In here, u bar is equal to, can you tell me what it is? So remember what it is? It's just the straight line connecting 2 points, 1 and minus 1, right? And I chose it to be in the simplest possible form, and this is simply z. Okay? Off you go. Substitute this into the equation, see what happens, and see what you can do, what you can figure out. So what is the solution of this equation subject to the boundary conditions at the first region first. So I'll let you try to find it, and once you get the solution, we will discuss it, right? And I will check that it is correct solution, and then we will move on after we agree that we found the solution. Okay, up to you. So take this, substitute that, see if you can find what psi hat is. And I will not show the full solution, but I will summarize what you get once we discuss and once we agree that everything is correct for each of the regions. Okay, so once any one of you gets some potentially correct answer for region A, let me know. I'll have a look, and if correct, I'll copy it on the board and we will discuss it. And we might also do, if any of you have any difficulties, right? If you have any difficulties finding the solution or not really knowing where to start, let me know. I'll come and help you individually. Just raise your hand.
Can you start from here to anytime?
So basically this is an equation, right? So, and u bar is equal to 1. So you replace u bar with 1 everywhere. So what happens to this term?
This will be 0.
It will be 0. So therefore you'll get 1 minus c multiplied by that. So this is never 0. So therefore this has to be equal to 0. So that that's the equation that you need to solve. Okay? So see if you can solve it. If you can't, I will just... Yes, but finish with A first, and then we will go to the rest. Okay? One region at a time. So don't try to solve all 3 regions. Just see what happens in the first region, in region A. Then we will touch base. So we will try to check, so to realize what is going on, what the solution looks like. And once this is done, then we will continue to the next region. Okay, so first we need to get an idea of what needs to be done, and then we will just duplicate these steps for the rest of the regions. So by now, at least I expect that everyone derived the equation. So how will the equation look like? So what do we need to solve here? So what equation are you solving? So what happens to Rayleigh equation in the first region? Okay, 1 minus c in the first bracket. Is it 0? Can it be 0? No. All right, so in the second brackets you have second derivative of psi minus alpha squared multiplied by second derivative over a constant is 0. And the right-hand side is equal to 0. So the first multiplier is non-zero. The second multiplier involves psi and second derivative of psi. And the rest are zeros. So you have a product which is equal to 0. And one of the factors in that product is non-zero, meaning that the second factor must be 0, right? So therefore, we will get d squared psi hat minus alpha squared psi hat 0. So that's the equation, right? Does everyone agree? Okay, I got rid of all unnecessary terms. So 1 minus c is not really relevant. That's what is relevant. Okay. See if you can find the solution of this equation. And clearly, this is a linear ordinary differential equation of the second order with constant coefficients. And alpha is assumed to be real. That's how we introduce it. So alpha squared is also real, and minus alpha squared, obviously, negative. So what's the solution for this equation? All right, I heard that somebody told me that the solution is sine and cosine. Does everyone agree? No, not at all. So I said, I hear that somebody is saying that it is a linear solution. And I disagree with that. If it is linear, then second derivative disappears and this is not 0. No, it cannot be linear. So what else is there? exponential, right? Exponential solution. And I'll just take a moment and tell you one thing which I always teach my undergraduate students. If you have a linear ordinary differential equation with constant coefficients, the only solution ever possible is exponential. There could be no other solutions to this equation. You might be surprised by this statement because you were told that a linear solution can be can be added to the family, and then trigonometric solution, sine and cosine, could be added to the family, and you actually quoted them. And I claim that I'm still right, and what you say is not wrong, but not right either. So why? So there is a very, very simple explanation to what I'm just I told you. What you have here is a sum of terms. And this sum of terms is equal to 0. That means that terms cancel each other. They can only cancel each other if they individually have the same functional form. Right? You cannot have apple and orange, right? If I have apple and oranges, I give you apples, I still have oranges. If I have apple and oranges, I give you an orange, I still have apple. If I have only apples and I give you apples, I have nothing. You know what I mean? So these two terms, to be able to cancel identically as we have, must have the same functional form. But this contains the function, that contains the derivative of a function. So derivative of a function has to be of the same form as a function. And the only possible candidate for this is exponential function. Only exponential function remains itself upon being differentiated. Okay? But you tell me, well, okay, but what about trigonometric functions, sine and cosine? We were taught from year one in well, maybe high school, that it also solves the equation. Yes, but trigonometric functions are exponential functions. They're just complex exponential functions, so they're still exponential functions, right? And what about constant? Constant also, in some cases, or linear function can be a solution for this equation. Well, exponential function, where exponential is raised to a 0 power, is a constant. So it is also, constant is also exponential function. So all of them are essentially exponential functions in disguise. That's what we need to remember. So anyway, the solution of this particular problem is exponential, right? And the reason for that is we have negative coefficient here. So whatever your favorite way of solving this equation is, so I will not go into that by writing characteristic equation, say lambda squared minus alpha squared is equal to 0, or something like that. So I'll leave it up to you, so it is not part of this subject. So the solution will be, and I just want to be consistent with my notations. So you will have a e to the power minus alpha z plus a1 e to the power plus alpha z. So that's the general solution. Now we need to determine the constants. And the constants are determined from boundary conditions. So we have only one boundary condition relevant in this case, because the domain is limited to z being greater than 1, and boundary condition is, which belongs to this region, is at z equals infinity. So therefore, from this, what can we say? A1 has to be equal to 0, because otherwise it will blow up, right? So therefore, this term is not even there, so I will not bother writing it. So that's the solution. Now, we used we solved the equation, we applied the boundary condition, whatever boundary condition is available, but the other boundary condition is unreachable because it is beyond 2 corner points. So therefore, the next thing would be to apply the jump condition. For the jump condition, we need to know the solution in the second layer. We cannot apply it yet. So therefore, the next step clearly will be to consider what happens in the second layer, right? And you need to write an equation for the second layer and solve it. And the second layer will not touch either of the boundaries. It will not go to plus infinity or minus infinity, so therefore it will only have a chance of satisfying the jump conditions, right? So, all right, go ahead, tell me what it looks like. So what the equation looks like and what the solution looks like. So one suggestion is that it is the same. Does everyone agree? So the same what? Equation or solution? Equation is the same. All right, I will be pedantic and I will write it down, so you will still get the same equation. And what is the solution then? So the solution, general solution, is still the same. So I will just make sure that I use different constants because obviously we are in different regions, so the constants are not the same, right? So, and then I will have, so what do I have here? So I have B and C. So I have B e to the power minus alpha z plus C, but make sure that you do not confuse that with a small c that we introduced previously. That's capital C. C e to the power alpha z. So, can we say anything about these constants? Can we say that any of them has to be 0 or 1 or whatever, just by looking at that and trying to see what the conditions, what the conditions are at this stage? Remember that we have to have the jump conditions enforced. And the jump conditions link what happens here with what happens here, and what happens here with what happens below. Right? What happens below, we don't know. We haven't solved it yet. Agree? So, all right, so at this stage, just make sure that you agree with me. If you don't understand what I'm saying, just raise your hand and I will explain once again in different words, but that's really important. That's procedure. So at this stage, you solve this equation, but there are no conditions yet that you can apply straight away. Because the matching conditions, you can apply matching condition with the first layer because you have information, but that will result in some sort of equation. And that equation will only be a single equation, right? So therefore, we will not be able to get both constants. So for this reason, what we will need to do is to leave it as is, because right now we don't have enough information, not to have full information about the matching top and bottom. Bottom is not computed yet. And boundary conditions are not reachable at this stage. We're in the middle, sandwich in between, right? So therefore, what we will need to do is simply live with this general form for the time being. We can't do much. Is that clear? Good. All right, so we did our best. Now let's go to the next layer, layer number 3, or I called it layer
C.
What is the equation there?
C.
So you can see the pattern. So equation is exactly the same. So the solution, therefore, is also the same, right? Different constants, of course. And I'm running into problem here because I already used D for differentiation. So therefore, I need to introduce something else. Okay, cannot do that. So what do I do in my lecture notes? Oh, I confused myself there. So I will introduce E. E to the power minus alpha z plus f e to the power alpha z. Now, can you tell me, and as a matter of fact, I will, can you tell me if you can determine any of these constants? Because right now we have an opportunity to touch some boundary conditions, at least one boundary condition, right? Because this region extends to the boundary. Boundary is at minus infinity here. So what do we need to ensure? So we need to ensure that this solution does not blow up. If we go to minus infinity, then this will become infinite. So therefore, this cannot be there, right? So therefore, so I'll just erase this and rewrite it neatly. So f e to the power minus alpha plus alpha z. Okay? Is everyone with me? Good. So, okay, so now how many unknowns do we still have? We determined the structure of the solution. So we need to determine A, B, C, and F. 4 constants. We need 4 conditions. How many jump conditions can we get? So we have 2 jump boundaries, right? 2 jump boundaries. And on each of those boundaries, how many can we have? 2. So 2 times 2 is 4. So the system is well defined. 4 unknowns, but we can come up with 4 equations. So let us write them down. So, and I will let you do that. So essentially what you have is the jump at z equals 1 and the jump at z equals minus 1. So therefore you need to substitute the values of z equals 1 and z equals minus 1 into equations which come, or expressions which come from these 2 equations. And this is probably the most time-consuming and tedious part, because these equations are quite long, right? And you need to make sure that you evaluate them at one point and another point, right? 2 points. So that's what you will need to focus on. So, and if there are any algebraic errors, then they likely would come from here. So that's from experience. So that's the tedious part. So, but I need to leave it for you so that you need to practice. So therefore you have these equations, you write them the way is suitable for particular choice of u. So that will be simplify things a little bit. And then once you have these 4 equations written explicitly, you just need to go ahead and solve them. Okay? So one advice I can give you, it's just a common practice when we are talking about jumps. So if we have a jump at this level z0, so what z0 is either 1 or minus 1 in our case. So if we are talking about something happening on top of this interface, the notation is that this is z0 plus 0. Okay, that's just notation. So therefore, this is f of z plus 0. And what happens under interface, the notation would be similarly f of z minus 0, or z0, z0 minus 0. So that's just to distinguish, because it is literally, it is the same point, but you approach it from the bottom or from the top. Okay, so if you need that, so that's my suggestion. That's not to get confused. If you write f of z0 everywhere, so it is confusing. So which layer do you belong to? So this way it makes it clear that you are approaching this interface from the top or from the bottom. That's from the top, that's from the bottom. Okay, so I'll give you some time to write down 4 equations. Then I will copy them on the board. So check, make sure that everything is correct. You copy it from me back, make sure that you have it correctly, and then we will go ahead and solve them. Just expression, without solving, without just writing it down. Did you get it? All right. Let me just copy it on here. So maybe you can do it yourself. So you just could copy it, what you get on the board. So we will look at it and discuss. Can you do that?
Yeah. What's the word if I don't?
Oh, that's fine. We need to start somewhere. We need to see what the difficulties are. If you're wrong, then chances are that many others will be as well. Take some. Sorry, only jump condition. So the final, can you be, because we already have all these. Do you have expression in terms of exponential function? Not about...
So I was deriving the boundary conditions first.
So boundary conditions are already given. So we already implemented them. So what I'm talking about, jump conditions. So what I'm talking about is substituting the values into these equations.
Oh, so I was just doing...
Okay, you haven't done it yet. Okay. Yeah, all right. It's fine. So what I'm talking about is what happens when you substitute the solution that we obtain into this equation at z equals 1. So can anyone tell me what actually happens? So you have the value on the top, you have the value at the bottom, so the difference between them equal to 0. So the easiest way to write this equation is to simply evaluate this above, evaluate and make it equal to the same equation evaluated below. That would be probably the easiest way of writing it. Okay, so substitute what we have into this equation, substitute z equals 1, and then do the same things from the second region. So evaluate the same thing using the solution from the second region and evaluate it at 1. And see what happens. Okay. Is there anyone who completed that? Just without solving, just writing. So we understand how mechanics works. Anyone? So it's taking a little bit of time. So, and I suspect that maybe not everyone quite understands what I'm asking for. So, and If this is the case, please ask questions. So I would imagine that it would take you 15 seconds to do that, 30 seconds, but it takes already too long. So does anyone want to volunteer to go to the board and show what they've done, or just do things under my guidance? Don't be afraid. Anyone? Don't be shy. We need to move on. Thank you. Yep. Just start copying on the board, right? And explain what you're actually doing. And I will tell you whether it is right or wrong. If it is wrong, then I will take over.
I substituted this with this.
So we take this, that's the solution from the first region, right? And what we need to do is to substitute this and this. So if we're matching two layers, the first layer and the second layer, so and what is Z?
Z.
Z. Yes, we're evaluating that at the interface. What's the value of Z at the interface?
Is it Z? No.
No, that's 1. Z equals 1. So the geometry is such that the interface is at Z equals 1. Okay, so therefore Z is not Z. Z is equal to 1. Just with your pen, yep.
Minus.
Okay, so let me just double check.
This is my favorite.
Yes, I see. And all right, but that is evaluation. Sorry, not too that fast. So this is evaluation of the condition. So that is the evaluation of this condition, right? So what you did, you took this expression and you substituted the values of u bar and psi into this equation at z equals 1, right? And you use the two types of functions. One function is evaluated at above z equals 1, and the other one is below that, okay? So yes, thank you. That's exactly what we need to do, right? So does everyone follow us? Thank you. So basically that's what is to be done. So you take this expression and you substitute everything you can from the top layer. And you substitute z equals z0. In this case, z0 is equal to 1. Okay? And if you do that, you will get some expression. And the expression will look something like that. So there will be some factors which will cancel, right? So, and the rest will still be there. But the starting point is write down everything without canceling anything. And then once you wrote it down explicitly, then see what is actually possible to cancel, if anything. Okay? So the point is, don't do much in your head. Write it down explicitly, so how it appears in the equation. And if there are some simplifications, then that will be the next step to introduce. Don't try to simplify anything in your head, because you will get confused and make a mistake. So that's just the procedural advice. Okay? So, and now I just take the liberty of erasing this and just writing it more neatly. So the final result will look like that. So not that what was there was wrong, but I just want to write it neatly. So, sorry. So we have, so this expression here, du. So u is equal to 1. What's du? 0. So this term disappears, right? In the top layer, this term disappears. And what about this one? It is 1. This is c, so it is 1 minus c, minus in front of it, right? What about deep psi? It's derivative over e to the power minus alpha, right? So therefore it will be minus alpha. So therefore we will get 1 minus c multiplied by the square bracket. I'll just preserve the syntax the way it appears here, but this term will be gone. This will be minus in front of it, so there will be minus in front of it, multiplied by derivative of that, right? And this is e to the power minus alpha x multiplied by a. Differentiated, you will get a multiplied by e to the power minus alpha multiplied by alpha, right? So therefore, we will get, yep, one minus c multiplied by minus alpha multiplied by a e to the power minus alpha. Agree? Is there anything else which comes from here, from this equation at the top? Anything? No. All right. So this is what we have, and that will have to be equal to the same expression evaluated below it. So below it, u is equal to z. So what's that? 1. And this is so 1 multiplied by e to the power, the second expression,
Done.
alpha z multiplied by b, so this is not 1, this is b, plus c multiplied by e to the power alpha z. Agree? Okay, what else is there?
Right.
So this is z minus c multiplied by deep psi, right? So z minus c, but what is z? It is 1, so this will be 1 minus c again, right? Taken with minus 1, minus sign in front of it. So that's what we will have here,
Yeah.
right? Multiplied by derivative of this. And what is the derivative? Minus alpha multiplied by b e to the power minus alpha, and z becomes 1. All right, so that becomes 1, and that becomes 1. That becomes 1. And plus alpha c e to the power alpha. All right, so that's how it appears in the first place. Agree? Okay, so we finished, right? So this hour is finished. So basically that gets you an idea of what needs to be done. So that's one of the equations. It is quite tedious, but it is possible to derive it. So if you have everything in front of you, so the advice for the test would be, of course, that you have to have it on the page in front of you. The problem I'm facing here, because I have to jump back and forth. You cannot afford that in any exams or tests conditions, right? So you have to have the whole equations in front of you. So make sure that you copy all the information needed onto the same page. Okay, so that's what we need to do. So that's one of the equations. So, and we need to come up with the 3 other equations. Okay, so that will be our task for the next, well, few minutes after the break. Okay.